This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Alright, good morning everyone. So today we will continue talking about tools for frequency domain analysis and design. So we will introduce body diagrams. I suspect that most of you have seen body diagrams maybe in signals and systems or a similar subject. So we will just revise some of this material. So we will introduce what body diagrams are, and then we will present several examples of how to plot these diagrams, and also interpretation. We will also learn how to interpret some of these diagrams, what they mean, right? So here's the outline. So we will first define what body diagrams are, then we will just briefly show how to do it via MATLAB, how to plot them via MATLAB, and then we will go through various examples, properties and interpretations of these diagrams. And then we will wrap up. Later on, in the rest of the subject, we will be learning how to use these diagrams for analysis and design. So at this stage, we just want to introduce them. Right. All right, so what we saw in the last lecture was that if we have a stable linear time invariant system described by its transfer function h of s. If we hit this system with a sinusoidal signal of a certain frequency omega, then the output in steady state will be a sinusoidal signal of the same frequency omega with some phase shift, which is captured by this phase of h at the frequency, j omega, and also scaled by the magnitude. So the amplitude of the output signal in steady state is scaled by the amplitude of this transfer function at that frequency, and also the phase of the output signal will be changed, shifted by the phase of h at frequency omega, where what I'm using here is h evaluated j omega is basically h of s when I replace s by j omega, right? And I can represent, so h at j omega is a complex number that depends on omega. So I can represent this complex number as its magnitude and phase in this way. So you can immediately read out, if I tell you what the input signal, sinusoidal signal is, you can calculate what the output of this system would be, in steady state by finding the magnitude of h at j omega and multiplying the input amplitude by that number. That is the output amplitude. So amplitude scales with magnitude of h at j omega, and the phase changes exactly by the amount coming from h evaluated at j omega. So you can immediately write the steady state output if I give you sinusoidal input, right, in this way. All right. So that's what we covered in the last lecture. By the way, for all of this, we assumed that the system is stable, right? Okay, so we also saw in the last lecture that it is convenient to plot this h of j omega in the complex plane, where we represent a real part of h of j omega, the imaginary part, as points that change with omega. So omega is then the parameter in this graph, and we can also represent it in polar coordinates. So for every given omega, I can find the magnitude and phase of H and plot them in the complex plane. So this led to, frequency response plots, and we will work more with these objects when we introduce body diagrams. So that's what we did in the last lecture, and this is a starting point for today's lecture. So what we want to do today is we want to look at a different way of plotting this guy. So in the previous lecture, we presented this frequency response plot, right, in complex plane. Now, body diagrams do the same thing, but using two plots rather than one plot. What they do, they basically concentrate on plotting just magnitude as a function of omega, and then phase as a function of omega. So these two plots, body plots, are exactly the same thing as the frequency response plot that we saw in the previous lecture, except that the frequency dependence of magnitude and phase of H are explicitly represented as functions of omega. In the frequency response plot that we showed last lecture, these are implicit. This dependence is implicit because we don't know what omega corresponds to different points of the graph, right? Okay. So we will use these plots, actually even when the system is not stable. So note that I introduced the concept of frequency response for stable systems only. But actually mathematically, I can plot this object just by replacing S by j omega and just plot it, even if the system is unstable. So why do we do this? Well, because it turns out that these objects are useful for analysis and design, even when the system is unstable. So we can just ignore now stability when we plot these things, right? Sometimes these plots are called Nyquist plots. So what we called frequency response plot in the last lecture, if the system is unstable and I plot it, it's just Nyquist plot, right? But we will learn how to, what particular transfer function to choose in analysis and design of Fulex systems. We will talk about that later. All right, so what we want to do now, we will ignore now whether the system is stable or unstable. I just have a transfer function. I substitute S by j omega, and I want to plot these things, right? I want to plot this object, H or j omega. All right, so this leads us to the concept of body diagrams. So what are they? It turns out, well, they are two diagrams rather than one. So what I will plot is this thing, 20 log of magnitude of H, j omega. And by the way, the unit that we measure this object with is decibels. And versus logarithm of omega on the x-axis. And then here we have phase of H j omega versus logarithm of omega. This is measured in radians per seconds, and this is measured in degrees, usually. All right, so why do we do this? Well, I will present that in the next lecture. This taking the logarithm rather than the magnitude itself is really helpful when we want to add graphically different diagrams. I will explain why we are doing that in a moment, but logarithm of the product is the sum of the logarithms. And that's the property that we will use, and this is why we plot it using the logarithms. Why we use logarithms of omega? Well, it gives us more compact diagrams because this logarithmic scale can cover a much broader, wider range of frequencies which are of interest in design and analysis. So it's just more convenient to work with logarithms of omega. Why this square? Well, this 2 here, right, comes from just historical reasons. It's like a square of a symbol is like a power, so they were trying to plot powers. And, that's not so important. Think of this as a convention, which we will use to plot, logarithm, 20 logarithm of magnitude of H and just phase versus logarithm of omega. This is what body diagrams are. Now, obviously, whenever I give you a different transfer function h, these diagrams would look different. So what we need to do in today's lecture is introduce several of these examples, look at examples and some properties that will help you quickly sketch these things. All right? So that's what we want to do today. Why logarithm of magnitude? Well, I remind you that, typically transfer functions that we are dealing with are rational, right? So there are some terms in the numerator and some terms in the denominator. We can often write this denominator and numerator as a product of some simple terms corresponding to poles and zeros. So it can be s plus p1 times s plus p2, right, in the denominator, right? So you can rewrite this transfer function, rational transfer function, as a product of simple terms. So obviously then the question is, well, if I have body diagrams of these simple terms, how can I quickly come up with a body diagram of a complicated transfer function that is a product of these terms? Taking a logarithm helps. Why? Because product, which we typically need to deal with in transfer functions, when we take a logarithm, becomes the sum of logarithms. So logarithm of a product becomes sum of the logarithms. And also, product of phase of a product is a sum of the phases. So what does this mean? If I have basically two transfer functions and body diagram, I know what body diagrams are of these two transfer functions. Then the transfer function consisted of the product of the two simple transfer functions is the sum, basically a graphical sum of the two simple body diagrams. So I have a simple body diagram of one transfer function, simple body diagram of another transfer function, and I can graphically add them to get the body diagram of their product. And that's a very convenient property that is very, very useful for analysis in design, right? So, but this sort of small analysis of properties of complex numbers really motivates why we look at logarithms in plotting these things. All right. So by the way, transfer function can be written in this manner, right? So any transfer function might have a number of integrators. It may have a number of poles, a number of zeros, and it may have some constant k that comes in front. So pretty much any transfer function you can think of that we deal with, rational transfer functions, can be represented in this way. So then, obviously, because now we have this additive property, what we can do, we can say, let us concentrate on plotting what is the body diagram of just a constant k, what is a body diagram of just an integrator or an integrator to power k, what is a body diagram of a term that looks like this, that has a real zero or real pole, or we can also have complex zeros, complex poles, right? So going through all of these different cases would then equip, it's like Lego, right? You have simple Lego blocks, right? And you would be, if you learn, what properties of these simple Lego blocks are, you can create anything you want with those simple Lego blocks. So we need to understand what are the simplest body diagrams that you can come across. And then any other more complicated body diagram can be obtained by additive property, by adding these things up, to obtain body diagram of arbitrary transfer function. And this basically analysis here, sorry, what's this? So this analysis here tells you, well, if we look at, let's say, what is just a body diagram of just constant k, right? What is a body diagram of just an integrator? What is a body diagram of zeros or poles appearing in the transfer function? Then we would be able to create any transfer function body diagram, right, from these simple ones. All right. So I already explained this additive property and why we are doing it, why we introduce body diagrams. Now, these tools are really invaluable. The crown achievement of this subject is so-called loop shaping methods for compensated design, control design, and these are based on body diagrams. So body diagrams will be essential for design, right? We will now plot body diagrams for a number of simple transfer functions. Why simple transfer functions? Because more complicated transfer functions that can be written as a product of these simple transfer functions can be easily obtained by adding these simple body diagrams together. Yeah. All right, so let's now first say, well, how do we do it in MATLAB? Well, these are the commands. Basically, if you have a transfer function like this, you can define its numerator and denominator in the transfer function, and then it says just plot body of this transfer function defined by this numerator and denominator. These numbers here are exactly the coefficients in the polynomials in the numerator and denominator, right? It's very simple. So MATLAB can do this very quickly for you. Now, why would we spend some time learning how to do this like by hand? Because it does give you intuition without MATLAB, right? So if you know how to do these things very quickly, first you can guess how to go about design or do design properly, like by hand, maybe without MATLAB. But also it gives you a proper interpretation of the output that MATLAB gives you. Sometimes MATLAB gives you something, and if you don't understand the theory behind, you won't understand what it's giving you. Right? So we need to do this for both reasons. Right? So we will now, for the rest of the lecture, go through a number of body diagrams, their properties, and interpretations. Right? So let's go one by one. So suppose, so you can't think of a simpler transfer function, right? So the transfer function is just a constant, positive constant, right? So basically, your system is static. So what is this system? Well, if this is the input, the position here, and that's the output, well, for a given input, there always corresponds a given output. So if I then say, let input oscillate sinusoidally, well, output would oscillate, also sinusoidally. This example actually would be more appropriate if the G was a negative number, because when I'm moving here up, the other side moves down. So that would be like but it's the same idea, right? So this is a transfer function. So for the same input, you just get the same output. Note that in this case, the output of the system is just scaled, the magnitude is scaled by the constant, which is a transfer function. What this constant corresponds to, if the pivot is right in the center, then the constant is -1. As I push this by a certain amount, this side goes by the same amount but in the opposite direction, right? If I put the pivot here, then the constant would be negative and larger. If I put pivot here, the constant is negative and smaller, because large excursions here result in a smaller amplitude there, right? So that's the transfer function. It's simple. This is a teaching tool, by the way. So if I now plot what is so the green curve here is the input to this simple system, and the output, obviously in steady state, we immediately get steady state. There's no dynamics. So the red is the output. So what is the frequency response of this simple system? Well, G of j omega, where G of s is 2, right? Well, G of j omega is also 2 for all omega. So basically this corresponds to a single point. For all frequencies, you get a single point. And that's your frequency response for this simple system. If we write down now, okay, what are the body diagrams for this simple system? Well, we need to first find the magnitude. So we need to find 20 logarithms of 2, right? And we need to find the phase. Since it's a positive number, phase is 0. So phase is 0, and then 20 logarithms of 2 is about 6, right? So that's measured in decibels. So this can now, you can now connect quickly. This is the frequency response curve in the complex plane, parametrized by omega. That's what we were plotting last lecture. And these are the body diagrams corresponding to the same problem, to the same transfer function. Note that in this case, phase and gain do not change for any frequency. And this is indeed the simplest situation you can think of. Here is the same thing, just with a negative number. Now, the only difference here is what? Note that the sinusoids here now are opposite, going in the opposite direction. That's exactly like the seesaw here, right? So by the way, if I put the pivot right at the end, and I say this point here is the output, then you will have positive constant, right? Because when I'm moving this side in the positive direction, this point also is moving in the positive direction. That would be the transfer function in the previous case. And now the transfer function is exactly the seesaw, because it's a negative gain. So what is the only difference between the previous case? Well, now the frequency response is just -2, and now I have phase is, pi, or 180 degrees. But I still have magnitude is the same as before, because I take the absolute value of -2, right, and plot log 20 logarithms of that. So magnitude didn't change, but the phase changed, all right? So, and then you can also connect to in time domain. This is what happens in steady state, right? All right. Now, if we look at a differentiator, by the way, this is a non-causal transfer function. We don't care. We don't care about that, because what we are interested in here, we are interested to plot body diagrams of simple constituent transfer functions, and then any other transfer functions will be written as a product of these simple terms. So you can easily generate a causal system through multiplication of non-causal operators and some causal ones, right? So that's why we are here interested in differentiator. Well, what is now g of j omega? Well, it's just j omega, because g of s is s. I substitute j omega for s, so j omega is just j omega. Now, what's the magnitude? Well, magnitude is just the amplitude of omega. And what is the phase? Well, it's 90. If you look at frequency response, well, for positive omega, it stays on the imaginary axis. There is only imaginary part. There's no real part here in this gj omega. So the phase is always 90 degrees for positive omega. By the way, what I didn't emphasize is in frequency domain, when we were plotting frequency response, I said we will plot it between minus infinity and plus infinity. Here we are just plotting from 0 to plus infinity, right? But we said we can mirror image everything for minus negative omega. So everything is symmetric with respect to the real axis. So it's not a problem to just ignore that for time being. So for positive omega, this is the frequency response. Basically, g of j omega is just j omega. So we basically just exchange omega with just our on the imaginary axis. And this basically says, well, look, the gain as we increase omega obviously would grow, right? And then the phase will be always 90 degrees. Now, what can we learn from this gain phase characteristic? Well, for a given omega, if I give you omega, I don't know, 100 hertz or 1000 hertz, I can read out what would be the phase shift in steady state, or phase shift of the output in response to the input of frequency 100 hertz. But then I can also read out what will be the magnitude, the amplification factor in this case. So note that differentiator here would amplify high frequency signals. The higher the frequency, the output in steady state would have the larger amplitude, right? So what does this mean? Differentiator amplifies noise. Noise is typically very high frequencies. So differentiator amplifies noise. This is an issue for design that we have to bear in mind, all right? Let's consider an integrator. Well, if you look at an integrator, so integrator, when we substitute instead of sj omega, we get 1 over j omega, because integrator was 1 over s. But we now multiply by j, denominator and numerator, so I get minus j over omega. So note now that when omega is small, the amplitude is actually very large, because I'm divided by omega. When I'm dividing by something close to 0, the amplitude will be very large. So omega close to 0 would be actually points that go to infinity, right? And omega very large means that I'm dividing something by infinity, so I'm approaching 0. I'm still always on the imaginary axis, but the parametrization of omega is the opposite from the differentiator. So what does this mean? Well, integrator would basically amplify very low frequencies, right? For low frequencies, we get this amplification factor here, right? So, because just think about it, I plotted here everything from omega equal 1, but I can, because this is a logarithmic scale, I can keep going, you know, omega 10 to minus 1, 10 to minus 2, etc. This will keep going, right? So this is basically saying that for a small frequency, the amplification factor is infinity. Right? But for large frequency, in steady state, you know, for different omegas, amplification factor is reduced. So basically, think about an integrator as having some sort of, I don't know, inertia in the system. So if you try to shake it with a sort of sinusoidal signal set the frequency, the output in steady state will have attenuated amplitude, right? The higher the frequency, the smaller the amplitude in the steady state of the integrator. All right. So by the way, each of the points. So if I say what is the point on the body diagram that corresponds to omega equal, let's say, 10. This is the point where omega is 10. Well, I can read out the amplitude, magnitude, and phase at that frequency, and then I can use polar coordinates to find a point on that plot above that corresponds to that point in body diagrams. There's a one-to-one relationship between points on this frequency response curve with points that correspond to different omegas here in these diagrams, right? So these are one and the same thing, just represented differently, right? I see lots of confused faces. So are there any questions? Okay. All right. Maybe I just haven't woken up yet. Maybe. All right. What's the body diagram of real zero? So if I just have this transfer function, I substitute instead of Sj omega, then now I have real part and imaginary part in frequency response. So real part is always 1 for all frequencies, and the imaginary part changes depending on omega. In this case, the magnitude looks like this, right? It's basically square root of the square of the real part plus square of the imaginary part. And then the phase is arctang of imaginary over real. So that becomes arctang of omega itself, right? So what is the frequency response? It looks like this, right? And the body plot looks like this. So for small omega, note that the magnitude is close to 0, but that's in decibels. So what is the true magnitude of this transfer function? It is close to 1, because logarithm of 1 is 0. So basically these points here correspond to points where magnitude in the frequency response plot are close to 1. So basically you know that for omega 0 you are starting from 1 on the real axis, and then for small omega you are close to that point. And those points correspond to this, these points here. What is the phase? Well, phase is close to 0, right? Because points of this diagram close to 1, you know, the phase is very close to real axis. I mean, the point that connects those points on the frequency response to the origin, that line will be sort of, so this is your frequency response, and you start from omega 0, you are at 1. As you increase omega, the point on the frequency response, you know, moves up. And then this line that connects the point to the origin makes, you know, a small angle with the real axis. So phase is small for small omega. So that corresponds to this part. Note, as we increase omega, that, you know, point goes, you know, to infinity, and then we get, you know, close to 90 degrees. Because, you know, as we're traveling, you know, on the frequency response, this line goes like this, and the phase is starting to approach 90 degrees as omega goes to infinity. All right, so what I already started talking about is that for small frequencies, I can set, when omega is much smaller than 1, so I can set it to 0, right? So obviously when omega is much smaller than 1, then this term here is negligible, so this is close to 1. Right. So this is one of the asymptotes in the body plot. What are the asymptotes? Well, in this case, note that this is one of the asymptotes for the magnitude plot, right? Because as omega goes to 0, it really converge to this line, straight line. And another asymptote is this asymptote, right? So we can calculate what these asymptotes are, right, from analysis directly on the frequency response equation. So if we look at what is the magnitude when omega is very large, then 1 is negligible. So I can take square root of omega square, right? And that's roughly like normal omega. So this is now becoming like a differentiator. This looks like a differentiator. So for large omega, this guy here, for large omega, behaves like a differentiator. If you remember, differentiator had that magnitude that just went to infinity, right? And for small omega, this behaves like a constant. So these two extreme cases we've seen before, right? But here we are dealing with a single transfer function. But in asymptotic cases, when omega goes to 0 or infinity, it either approaches, like it behaves as a constant for small omega or as a differentiator for large omega. And the phase, you can talk about phases as well. So for small omega, phase is 0, and for large omega, phase is 90 degrees. It's really like differentiator versus a constant, right? What is also useful when sort of plotting these things, note that reciprocal of a certain transfer function, so if I have a transfer function g of j omega, 1 over gj omega would really will have negative magnitude, because 1 over something is like this to power minus 1. Since we're taking logarithms, this minus 1 goes in front. So that's why we have this minus. And then phase is also with a changed sign. Right. So basically you just mirror image the body diagram. Why is this useful? Well, we now looked at a transfer function that looks like this. G of s is s plus 1. What about 1 over s plus 1? Well, we can use that rule. So 1 over s plus 1 is easy to draw now. So it becomes this. So it's just we mirror image with respect to the x-axis magnitude that we saw before. Right? So we don't need to, spend much time analyzing this. But this is also one of the sort of classical, situations that you find in different transfer functions. Now, look what it says. For exercise, find the time response of the system as we did in previous examples. In particular, what's interesting here is find the steady state, response, right, for a certain frequency. So if I, for instance, pick, so note, this is 10 to power 0. This is logarithm of omega, right? So 10 to power 0, this is 1, omega equal to 1, right? So for omega equal to 1 radians per second, I can read out what is the phase. So phase is what? It's minus 45 degrees, because this goes from minus 90 and 0, and this is right in the middle, right? So this is symmetric with respect to this line. So you are exactly at minus 45. What is the magnitude? Well, magnitude is close to 0, not quite 0. It's a bit smaller than 0, right? What does this mean in real terms? Well, this is a logarithm. So if the logarithm is negative, it means that the magnitude of the true transfer function is slightly smaller than 1. Because logarithm of a number smaller than 1 is slightly negative, right? So what this means, when I hit my system with omega equal 1, in steady state, the amplitude of the output will be scaled by a number slightly smaller than 1, and it will be shifted by minus 45 degrees. Minus 45 degrees. In steady state for a stable system. By the way, why I'm able to do this? Well, this system is stable because it has one pole with minus 1. So I can apply all those analyses from the previous lecture. Sometimes I said we will plot body diagrams for unstable systems, but for unstable systems, the interpretation of this steady state thing doesn't apply. Because unstable systems, might go up. The limit steady state behavior may not be well defined. You might be oscillating with larger and larger amplitude. The limit does not exist. Right? But for stable systems, like in this case, you can have that interpretation of body diagrams. Okay. All right, so are there any questions? I mean, I can see some people nodding, but if you're struggling with something, better stop me now, because this is very important stuff. I can't emphasize how important it is. We will use it over and over again. If any questions, please ask me now. Yep?
For the unsteps, we sketched the Nyquist. Is it the same thing? We cannot interpret anything from the Nyquist for the unstable, or it's something different?
We will plot both Nyquist and Bode for unstable systems, but the interpretation of steady-state behavior that I gave in the previous lecture only applies for stable systems. It doesn't matter whether it's Nyquist or Bode. Nyquist and Bode represent the same thing. It's the same thing just when you twist your eyes, but it's the same thing. Right? So basically each point on Bode diagram corresponds to a unique point on the Nyquist diagram. So that's why they represent exactly the same things. But Bode diagrams are easier to work with when we design controllers. That's why we introduced them. They're very, very useful when we design controllers. There was another question somewhere here, I think. Same question. Yeah, fully synchronized. Okay, good. All right. Win-win. Okay, so what I want to do now, I want to go through, you know, several. By the way, all of this that I presented are the most basic Lego blocks. But I might give you a house that you need to build from Lego blocks. So basically, I can give you a transfer function that requires you to add a lot of these simple terms, and then it becomes a bit, you know, more challenging, right? You need to be very comfortable with this material. You know, there is a big difference between, many of you have learned a second language, right? So when learning a language, the first stage is that you start understanding. So you read and you understand. That's the first stage. But then there is a second stage where you can actively use the language, right? So you understanding what I'm saying on Bode diagrams, you are just sort of understanding the language, but you're not able yet to use it. So you would need to be fluent, to use this analogy, you would need to be fluent in using Bode diagrams, because this subject takes them as a tool and uses them in design. So this, you have to, the difference between just understanding what I'm talking about and where you have to be to pass the exam is big. It's really the difference between passive knowledge of a language and fluency in the language. Okay? So because of that, I will now demonstrate at the end of the lecture what sort of things you might come across, right? And you know, don't be alert, but don't be alarmed, right? As our former Prime Minister used to say. All right, so so here is another example where I have a second order system. So what I'm plotting here is there is s squared plus 2 psi s plus 1. I basically decided that the natural frequency omega n is 1. So this thing here is like, this last term here is like omega n squared. And the thing that multiplies s should be 2 times psi times omega n. So if omega n is 1, so I'm plotting everything for omega n equal 1, which means natural frequency is 1. So if I plot now the magnitude and phase for this second order system, what you get is something that looks very different from what we had before. Note that you have this phase change from 0 to minus 180 degrees. By the way, before, when we had a single pole or single zero, the change was always between 0 and 90 degrees, or 0 or minus 90 degrees. Here the change is between 0 and 180, minus 180 degrees. Why is that? Because we have two poles. the number of singularities you have would give you the sort of range of that the phase will span, right? Potential range of the, obviously sometimes effects of poles and zeros can cancel out because we add things, right? But here in this case you have, this is the sort of change in phase. Note that what's plotted here is several plots depending on the damping. So when psi is small, you have this sharp, abrupt change in phase, and when psi is large, you have a smoother change in phase. Similarly, when you have small psi, you have this so-called resonant peak. And then as psi is increased, this resonant peak is suppressed. Actually, as psi tends to zero, what does that mean in terms of locations of the poles of this transfer function? They become closer and closer to the imaginary axis. You are closer and closer to marginal stability. Right? Psi, basically, what's psi? That's related to the angle that connects the pole, right, and the imaginary axis. So as this angle reduces, in other words, psi reduces, your pole is traveling towards the imaginary axis. And as you get very close, you will get very large resonant peak. So at this frequency, in this case omega equal 1, 10 to the power 0 is exactly omega equal 1. But omega n, natural frequency, is 1. I've chosen it to be 1. So note that this point is exactly the point where omega, which is the driving signal frequency, is close to omega n, which comes from the model. Natural frequency is defined by the model of the system, whereas omega is defined by the driving signal. So in other words, interpretation of this is when frequency of the driving signal is close to the natural frequency, we will exhibit resonant peak for small damping. What does this resonant peak mean? So if I hit my system with exactly that frequency, then in steady state, the output would be magnified a lot. So this is sort of, I mean, there are some, I don't know whether you like Mythbusters, but there was this sort of myth that if soldiers walk across a bridge, right, you know, in step, that would create a sinusoidal force at a certain frequency. They are saying, well, if you pick exactly the right frequency equal to natural frequency of the bridge, then you can destroy the bridge. Now, this myth was busted, but mathematically, or actually if you look at wind, what wind or earthquake can do, that's exactly what it is. It hits it with a sufficiently large force at the right frequency. Look up videos on YouTube what the wind or an earthquake can do to a bridge. Just sort of moves, and just sort of collapses, right? So the frequency at which you hit the bridge is really important. And if it is equal to the natural frequency, you can see that the amplitude of the output, which may be positioned somewhere on the bridge, will be magnified in steady state, right? So basically the properties of the system plus the driving signal could result in large amplitudes at the output when damping is low. When damping is high, you do not have this problem. So basically, when is the when damping is high? When the poles are very close to the negative real axis, right? That's when the damping is high, right? When you have two negative real poles, you will not see any resonant peak. Now, resonance, you know, sometimes you can hear it in microphones, right? So speakers, right? When you hear, you know, really this very loud noise, you know, basically the frequency, the input frequency hits your natural frequency. There's sort of a closed loop that sort of causes very loud output. That's the same phenomenon. There is a lot of, by the way, this resonant frequency is child on a swing. I can use very small force to move a huge mass if I just apply the force at the right times. In other words, I pick the driving signal frequency to be exactly the same as the natural frequency of my model, and then I can create very large swings with small force. Those are all examples of resonance, right? All right. Here are some examples. So if I have now transfer function that has a varying gain and then one stable pole, then as I increase gain, the magnitude would increase when it's positive gain. If it was a negative gain, it will go down, right? And then the phase doesn't change, right? So I'm just going through different examples. When I have 1, 0 and 2 poles, this is what happens. By the way, there are books that basically give you things like this. And this is the level at which you need to know these things. You need to know Lego blocks very well. So simplest body diagrams, you need to know very, very well. And you need to know also how certain parameters in your transfer function would affect phase and gain characteristics. So this is basically from Goodwin's book. Ogata would have lots of these sort of dictionaries of body diagrams. Please study these because you would need them. So you need to really be fluent in this. So these sort of diagrams are very useful. Also, I advise you check them with MATLAB and then play with some parameters in the transfer function and plot lots of these things just to gain intuition. MATLAB would very quickly calculate these things for you, but you will gain intuition about the shapes of these things. As you change zero location, pole location, damping, natural frequency, it's very useful in order to gain this fluency. This is like conversational classes when you're learning language, right? So you need to be really good at this. Here is one example of a transfer function. Look, if you have a transfer function with 2 zeros, 3 poles, and some zeros are stable, some are unstable, some poles are stable, some unstable, so all of the dashed lines with these arrows correspond to one of the constituent terms in this transfer function. So you can see from here, you have all these different terms, and then the full lines, blue lines, are really the added terms. So for this frequency, for instance, I read out what all of the green and black terms are, and I add them. So each of these green and black terms will have a certain value. So in that frequency, I just add these values, and I get, that's what my blue point is at that point, at that frequency. So that's what I mean by graphically adding these signals, these different transfer functions. These sort of transfer functions can easily be, you can in real life, you can have transfer functions that are order 16, 20. It can be anything, right? MATLAB would aid you in design and analysis, but for this subject, you do need to be very fluent in using these things and also sketching them. Like it's using the asymptotes that I presented earlier, you can quickly sketch if you know the basic Lego blocks. If I give you any more complicated transfer function, you can quickly sketch it in this way, right? By adding the constituent body diagrams. All right, so just want to remind you, body diagrams of complicated transfer functions can be obtained by adding amplitude and phases, right, of the simpler transfer functions. And we analyzed in detail some typical systems that frequently occur. You might get something that I didn't present. Basically, your level of understanding should be, if I give you any transfer function, you should be able to plot it, right? You should be able to understand, analyze it, right, and use it, right? And then body plots, actually what you could guess from this lecture, it contains a lot of information. Instead of saying it contains a lot of information, I can say it contains all information you need, because body plot and model of the system are analogous. Body plot is the model of your system. If you have your body plot, you have everything to know about the system. So when I write a differential equation, or I give you a body plot, it's the same thing. You know everything you need to know about the system. If the system is linear time invariant, right? Okay. All right, so in the rest of the subject, we will be using all these different frequency domain methods, Nyquist plots and body plots, to analyze stability, to analyze robustness, and then design in the end, okay? Questions? All right, I'll see you tomorrow. Thank you very much.
office hours next week because it's teaching
Um,
break.
I usually don't do it during the break
Right.
because I had to catch up on all the
Yeah,
stuff.
that's fine. That's fine. I'm just asking.
Yeah.
I had a quick question as well. It might be a stupid question as well. Didn't ask before, but here, when the football.
Oh, sorry. Yep, you're moving out. Yep, I'm moving out. I'm taking stuff.